our next speaker in this session is Marco Bertolini, who will tell us about hybrid conformal field theories.
All right, so first of all, I want to thank the organizer for giving me the opportunity to speak. And what I want to talk about today is a work in collaboration with Ilaria Melnikov and Ronan Plesser from Duke. So first of all, what's the big problem we want to keep in mind? Well, we want to understand the moduli space of 0-2 superconformal field theories. Why this? On one side, they provide their solutions of heterotic string theory with minimal supersymmetry in space-time. And second of all, they are an interesting moduli problem because they are, as we will see, tied to the mathematics of gauge bundles. So what's the most natural starting point for our for this kind of analysis? Well, let's take the large radius limit of CalabiYau. So we start with a CalabiYau threefold X. We take a holomorphic vector bundle on it with this condition that comes from supersymmetry or anomaly cancellation. And one may wonder, how does the moduli space that we say M look like? Well, for 2-2 models, we have this nice decomposition in where we recognize the splitting between the the complex structure moduli, the Kähler moduli, and these guys are the bundle moduli. Right, but this is clearly not enough in the sense that this description is valid only if the the scales of this supergravity geometric description is valid only if the scales are all the scales in the problem are bigger compared to the string scale, and we know that we have solutions that are provided by Landau-Ginzburg model where the target space is just a point. So definitely we want to understand more stringy features of this compactification. Or another interesting things that people want to understand is our non-perturbative correction instanton-like stuff come into play. Right, so how do we study such a moduli space? Well, in the last 20 years, a very powerful tool has been the gauge linear sigma model of Witten, and very briefly is a 2D gauge theory, weakly coupled, and whose low energy dynamic is modeled by the choice of the sort of coupling constant of the model, right? And when we study the phases in the Kähler moduli space, we see that when we study, the moduli space of the Kähler parameter, we see that it sort of divides into phases which have a different geometric interpretation, the well-known nonlinear sigma model, Landau-Ginzburg, and among which we have these hybrids. And these are the object we want to study today. So now we are in business for defining the goal of the work and therefore of this talk. So we're going to provide UV theory, so a UV description leading in the infrared to what we call a hybrid superconformal field theory, without, though, requiring that a GLSM embedding. And once we define this setup, we are going to develop and present a method, a technique for computing interesting physical quantities, such as the muscle spectrum. So a thing that I want to say, because it's important, we are going to talk only about 2-2 today, and it's going to be still, I will say, a non-trivial exercise, and not just an exercise, and we'll leave the 0-2 business for future work. So what's the geometric setup? We start with a Kähler manifold, why not, with a holomorphic function we call the superpotential that satisfy this condition. So dW is a holomorphic section of the cotangent bundle, And the critical point of W is a submanifold of Y0 B. They were required to be compact. And we call this condition the potential condition. So such as geometry has a hybrid model if locally the geometry for B is modeled by the total space of a rank n holomorphic vector bundle with some complex dimension D. So you might wonder, I mean, what's the point of this definition? Is that, well, we have the superpotential will suppress finite fluctuation away from what now will be called the base. So it's natural to that this local model will describe the low energy physics of this nonlinear sigma model. We want to relate this UV theory to a low energy superconformal field theory. So we need some requirements on our setup. So first we know that the theory at W equal to 0, so if we set the superpotential to 0, as this U1R cross U1L are symmetry, those are though broken by superpotential interaction. In order to make this symmetry actually a symmetry of the classical action, we require the existence of a holomorphic Killing vector that respects this condition, the superpotential, on which we can therefore modify this guy. And so these guys are not the same as this guy, but from now on we will refer to these guys as actually the R symmetry of the classical action. This symmetry can be anomalous unless the first Chern class of the tangent bundle on Y vanish, and therefore we require Y to be a non-compact CalabiYau. The last condition is that this holomorphic vector Killing vector we require it to be vertical. Therefore, in other words, the R symmetry doesn't act on the base. So we say that if this condition is satisfied, we have good hybrids. If not, we say pseudo-hybrid. So from now on, I'm just going to talk about good hybrids. So now we are ready to describe the action. And the action can be written in terms of 0, 2 superfields. So we have the bosonic superfield with the complex conjugate, whose lowest component is a map from the worldsheet to the target space Y. And with these fermions, and here there's the fermion 0, 2 superfield, whose low energy, with this lowest component is a section of the pullback of the tangent of Y. And here H is just auxiliary field non-propagating. So the action is written simply as a sum of two terms. We have a kinetic term and a superpotential term. And if we set W to 0, we just have a nonlinear sigma model on Y. So good. So now I think it's the point to say why actually studying 2-2 is actually not just an exercise, but actually can tell us something interesting. Indeed, even in the 2-2 locus, there are things, not everything yet is understood. In fact, even the question of how many 0-2 preserving exact marginal deformation are there is still too hard to be understood. So one may say, oh, OK, I'm going to take a step back, and I'm going to ask at least how many first-order deformation. And even this question for a generic point on the 2-2 moduli space is still too hard. In fact, techniques are available only at very special points or limits. For example, in Lander-Ginsburg, there's a technique provided by Katrin Witten back in '93. Or in this more recent work by Espinel, Melnikov, and Plesser, they sort of give a more systematic description of the counting of this deformation in large region and orbifolds, and they relate the counting between different phasing of a GLSM. But that's it, right? So we can imagine, so why hybrid is called hybrid? Well, because it's sort of a hybrid of a nonlinear sigma model and a Landau-Ginzburg, right? So it's definitely a more, maybe not the most generic phase, but if we think GLSM, a more generic phase that can arise studying a GLSM. So therefore, with this work, we can definitely increase the number of points on which we can extract interesting information. Right. There are other applications that is worth mentioning in which hybrid can play a role. For example, in this work by Alverson, Kumar, and Morrison, by localization techniques, they study the phase structural GSM in the abelian and non-abelian case. And in this other work by Kaldaru, Dissler, Harleman, Pantev, and Sharp, they look at the GLSM as a way to realize Kuznetsov homological projective duality. So here what I'm saying is that if one studies GLSM, then hybrid is definitely something that it naturally arises. Right, so what do we want actually to compute? Well, we want to compute the massless spectrum for a compactification of E8 cross E8 heterotic string theory based on a 2-2 hybrid superconformal field theory. The first observation is that the right-moving Ramond ground state correspond to massless fermions in space-time. And by supersymmetry, the knowledge of this is enough to determine the entire spectrum. And also, we are interested in on-shell states. Therefore, we need the left-moving and right-moving energy both to vanish. And it's just by looking at the algebra of the generator of the right-moving supersymmetry, we see that the kernel of, so L bar naught, I mean the right-moving energy. So the kernel of L bar is isomorphic to the cohomology of Q bar. So therefore, from now on, we will just restrict ourselves to the cohomology of Q bar. Another important point is that one might expect contribution from worksheet instanton wrapping non-trivial 2 cycles on the base. And so to avoid such troubles, we sort of define or put ourselves in the analogous limit, a kind of large radius limit that we call hybrid limit. So we take the B basically to be large, or in other words, the Kähler class of the base to be deep into the Kähler cone. All right, so for dealing with the left-moving part of the story, we can build, following the prescription by Silverstein and Witten, a left-moving superconformal algebra in Q-bar cohomology. I wrote down the entire algebra here, and but the main point is that we have a well-defined left-moving energy operator, as well as a U1L operator. So, and this V, just to remind you, is the holomorphic vector we required exists in like 6 slides back. Indeed, this is an n equal to 2 algebra with this central charge, where we can see sort of the contribution for the base. D was the complex dimension of B and of the fiber. Right, so as we said before, or many times, we are interested in compactification for string theory, right? So therefore, we need some kind of integrability condition on the charges of the states. And this is, the solution is the same as in Landau-Ginzburg theories. We need to orbifold by this symmetry, where J0 is the U1R charge. And then we need to sum over all twisted sectors. So for example, if you take X, so I recall that Y is the total space of X over B. If X is just a sum of line bundles, then this guy is just a discrete group Zn for appropriate n that follows from the geometric data of the model. But this is kind of nice because actually we can do more general things. For example, if we are given a X that is not technically a vector bundle, but is defined, the patching, the gluing is defined up to this gamma action, that's still a perfectly well-defined object for what are we going to compute. So we can study this, and we did, these more general Orbi bundles. So how is the computation actually is done? So I remind you, so mass spectrum, we established that we have to take the Q-bar cohomology on left-moving energy, on vanished left-moving energy space. So we use the fact that this operator Q-bar is written as a sum of two pieces, where Q-bar W contains the entire dependence on the superpotential, while Q-bar naught is the superpotential independent piece. So by use of the left-moving algebra we've written down before, we can sort of grade the Hilbert space by left-moving energy and U1L charge. On each of these Hilbert spaces, we have a well-defined double grade complex on which these two pieces act respectively as the vertical and the horizontal differential. So it follows that the full cohomology of Q-bar is computed by a spectral sequence. And here I just written down the first two terms. So we see the first, we just compute the cohomology of Q-bar, and then we take the cohomology of Q-bar W, cohomology of Q-bar 0, and then we take the cohomology of Q-bar W in the cohomology of Q-bar 0. All right, so to summarize a little bit, what we did is we provided in principle, a new class of UV theories leading to non-trivial superconformal field theories. I said in principle because actually we haven't built yet a model that is not obtainable as a particular phase of a GLSM. So indeed, one of the things that one would like to do is that, well, what are the criteria, if they exist, for such a model to be an embedding a special case of a GLSM? And now there are other future work that we're gonna, at least the first one, as soon as we're done with this paper, we will definitely look at 0-2 hybrid models, especially those without 2-2 locus. And I agree with you that there, we expect actually the real fun to happen, right? So we'll be looking forward to look to these more general models. And also another thing that, at least to me, it's appealing at least to probe is what could happen if we relax the condition for the hybrid to be good, which I recall was the R symmetry was not acting on the base. This has been at least mentioned in or studied from another perspective in this paper by Aspelund and Plesser, and will be actually really interesting to see if we actually can compute something and which kind of low energy physics can we extract from this technique in this more weird setting. So yeah, I stop here. Thank you very much.
So are there any questions?
The quantities you compute have translations into periods.
Sorry, say it again.
The quantities you compute, can you translate them into periods of some CalabiYau?
Oh, yeah, definitely. Right. So we definitely can compute the 2-2 moduli, right? So we can compute the if you have a GSM, what in large radius will be the complex structure deformation and the Kähler moduli, right? But in 2-2, those are boring because we know they are constant and they don't get corrected. So here the interesting things are actually the deformation of the bundle, right? H1 and NDT. So that's where we were looking at.
Any other questions? Comments? Right, if not, let's thank Malcolm again.
Thank you.